Awesome, awesome. Yeah, I think we can start. So, hi, am I audible? You can just confirm whether I'm audible.
Yes, I am.
Okay, okay, awesome. Yeah. So, welcome to today's session. Apologies, I have some bit of cold. Yeah, but we'll just move on to that. So, for today we'll be doing a pretty interesting topic. We'll be working around ckETH. So, as you are aware, over the last few sessions, we've been interacting with chain key technologies, and Kevin has been taking us through building on top of Bitcoin or integrating Bitcoin in our dApps. Yeah. So, for this particular month, we'll be focusing on now implementing EVM-based smart contracts on our dApps too. So for today's session, we'll focus on ckETH. Um, for next week's session, we'll see whether we can do calling an EVM-based smart contract directly from ICP canister, then etc. etc. Yeah, so we'll just get right into it. Getting started with ckETH. So, what are chain key tokens? I know you guys have been taken through, or we went through CKBTC a while back, and just to do like a sort of a recap on what chain key tokens are. So the current common way for blockchains per, to perform or to do multi-chain interoperability between different chains is through wrapped tokens. So what are wrapped tokens? Wrapped tokens are ideally just an underlying asset that is represented on a different blockchain. For example, a very um, popular or common example is wrapped Bitcoin. So we have wrapped Bitcoin that is present on Ethereum, that is ideally just a replica or a representation of the normal Bitcoin that we have on the Bitcoin network. So if I get lost, you can just or if you guys lose my audio, you can just unmute and say, yeah. Also, if you find my speech is not that clear because of the cold, you can also say. So ICP through chain key technology decided to create an alternative way of wrap tokens called chain key tokens. So the main distinguishing factor between the chain key tokens and the wrapped tokens is that we don't have an intermediary or bridge in between for the tokens. So how wrapped tokens work is they normally have a bridge in between them. So this bridge whenever you'd like to convert, let's say your Bitcoin into wrapped Bitcoin, they normally use a certain central authority, which is normally described as a bridge, to help conversion of the normal Bitcoin into wrapped Bitcoin. But then this bridging normally comes with a lot of security vulnerabilities, since a lot of people normally get hacked when it comes to them bridging their tokens, or rather converting let's say Bitcoin into wrapped Bitcoin, etc etc. So how ICP has implemented their chain key tokens is very different from the current wrapped tokens that exist. So the chain key tokens are normally backed one to one with a native token, which is held on chain with a smart contract. So ideally, how it works is this particular with the as you know, ICP has this particular feature called threshold cryptography. The chain key technology allows ICP canisters to hold signatures that will allow them to directly call smart contracts on other chain, or rather these ICP canisters are directly compatible with other chains such as Bitcoin, Ethereum, Solana, etc., because of the presence of the threshold signatures. So how it works is this particular chain key. This chain key technology allows the ICP and an ICP canister, or rather an ICP smart contract, to hold the native token. So um, a, a, a smart contract on ICP, or rather an ICP canister, can directly hold Bitcoin or Ethereum tokens. So this is where like the whole concept of chain key tokens come from. So just a few things to note is the implementation of these chain key tokens normally requires or utilizes the ICRC standards in order to make them compatible with decentralized exchanges and also other particular exchanges. So all chain key tokens, that is ckBTC, ckETH, or and the currently implemented ckERC20 tokens have have been implemented using the ICRC standard. So as you are aware, we have different forms of the ICRC standard. We have ICRC1, we have ICRC2, we have dApp, etc. So these particular chain key tokens normally use the most commonly used standard is the ICRC2 standard, yeah, because it has better features as compared to the ICRC1 standard. So we also have like certain requirements that are needed for all chain key tokens in order to offer them a high level of security and decentralization. So the first thing is the token has to be fully backed to the digital twin at all times. This is why the smart contract itself is the one that's holding the token, not like a centralized authority as the one that's used on bridging. Then the other thing is the token has to be traceable on chain. So when you see the transaction hash of that particular chain key token, it has to be traceable on chain. That is, you can like follow, you can see like where the token was transferred to and all that. And also the canister that's handling the token has to use chain key technology or chain key signature to manage the underlying token. So the different examples of chain key tokens are, we have ckBTC, we have ckETH, and we have the currently implemented ckERC20 tokens are ckPepe, cklink, and ckUSDC. I'm also hoping if we do get time in the course of this month, we'll be able to do ckUSDC. So now let's get deep into ckETH. So just a brief overview of ckETH. It's an ICRC2 compliant token, and it is backed one to one with ETH, and it is fully held on chain. It also does not rely. This is just a repetition of the things I had mentioned before concerning chain key tokens. It does not rely on a centralized bridge to facilitate the conversion of between ckETH and ETH. Yeah, so it's completely decentralized in the sense, if a user deposits or changes their ETH into ckETH right now, they'll be able to withdraw that amount of ETH they've changed instantly without having to wait for like certain permissions and all that. It also has the same value as ETH. And the main reason why you should be using ckETH and not ETH is because it's very fast and it's way cheaper as compared to ETH. So the cost of transactions is a fraction of the total cost of transaction on the Ethereum network. So it's very cheap. Yeah, so how does it work? So what happens under the hood of ckETH? So ckETH utilizes a number of canisters on ICP, and one particular helper smart contract that is deployed on Ethereum. So we have the first canister is called the minter canister, and this is the canister that is responsible for the minting and burning of ckETH tokens. I'm assuming that you guys are conversant with the concept of minting and burning of tokens. So for those that are not conversant, minting is just like creating the token, and burning is just like now deleting the token from existing. Yeah. Then the other smart contract that we have is now the Ethereum Helper smart contract, which it contains one function. Or it contains a specific function called a deposit function, of which a user calls it with a certain amount of it attached to it, and the receiver's principal address as an argument. Then once the function runs successfully, it emits an event that is named received it, which contains the sender address, the value of Ethereum that's been sent, or rather the value of ETH that has been sent, and the receiver as a payload. So ideally, once you call this is actually how you're now creating the ckETH token. So for example, I'm using like a MetaMask wallet. I'll just connect my wallet to the site. Then when I call the deposit function and attach some amount of ETH to it, I get to mint the ckETH to a particular principal address that is attached to that particular as an argument to that particular deposit function that I'm calling. The second canister that is used, it's a ledger canister. So the Ethereum Helper smart contract is deployed on Ethereum. For this particular session, we'll interact with the one that is deployed on Sepolia. So for the testnet version, yeah, because it's ideally it's just free. You don't have to use like real cash, which will be very expensive. The second canister is a ledger canister. It's called a ledger canister. So once a user has run this function and has called the deposit function and has already minted or has already sent the this specific amount of it to the contract with the principal ID attached. This particular canister, which is called the ledger canister, normally listens to the received ETH event that has been emitted, or that has been, yeah, ideally the received ETH event that has been emitted, and then it simultaneously fetches logs from different or multiple JSON RPC cloud providers. So the main reason that is fetching the logs from multiple Ethereum JSON RPC providers is to prevent a malicious actor from tweaking or changing like the contents of that particular function that has been that is being displayed here from the Ethereum canister. Not Ethereum canister, but ideally the Ethereum smart contract. Then once it has listened to this particular receive it event, it means so it's responsible for minting the specific amount of ckETH that has been that you see. Now when a user sends or calls this deposit function and attaches it to it, this particular ledger canister listens to the receive it event and means the specific amount of it that was attached over here as ckETH to the receiver's account on the ledger here. So if you do it practically, you'll understand it, but for now, just try to like, grasp the concept. So the ledger canister is ideally just responsible of listening to the logs, to the receive it event, then minting the specified amount of ckETH to the particular receiver's account. So this receiver's account is this particular principal ID that was attached as an argument when you are calling the deposit function. So withdrawing it also is performed by the ledger canister, this second canister, the ledger canister. So it involves just creating an ICRC2 approval on the ledger and calling the withdraw it function of the ledger canister. Then you have to have like a receiver it address as an argument to the on the minter. Yeah. Then as I had mentioned before, the minter canister is responsible for banning the ckETH tokens on the ledger canister. This is when the withdraw it function has been called. So when the when minting ckETH, this particular event is fetched, then the amount of ckETH is minted to this particular principal address that was attached. Then when burning ckETH, this particular function is called from the because as I had mentioned before, ckETH it has been implemented with the ICRC2 canisters ICRC2 ledger standard. So it contains an ICRC2 approval function, which allows the person to like call the withdraw it function and um, attach like the receiver's it address, so that when these particular tokens are burnt, or rather, yeah, they are burnt, it sends the respective amount of it to this particular receiver's address. Yeah. After that, it will create an Ethereum transaction and then submit it to the network. So let's go to now implementing it practically on our dApp. I'll send this particular presentation later. So if you just come and click the link to the documentation, it will redirect you to a tutorial that I wrote that will enable you to like get started with now integrating ckETH in your dApp in a matter of minutes. So the first step is to I'll just open my terminal. I hope you can all see my terminal. Yes, I think you can see my terminal. So I'll just open my terminal. So the prerequisites of this of getting started with this particular documentation is you have to have installed all the necessary environment requirements, of which I know most of you have. Then you have to have MetaMask installed in your browser and some Sepolia ETH testnet tokens in your particular MetaMask wallet. Then you also have to have like a basic knowledge of Rust, because I'm implementing using Rust. So in order to get started, I decided to create like a simple project template that comes with configurations for calling the helper smart contract on Ethereum, because it will take up some bit of time for you to like set up all the configurations and link it to like the Ethereum helper smart contract and call it. So I just created a simple starter template that does that for you on the front end. So your only work will be creating the backend logic. So the first step is to clone the repo. So I'll just clone it. Apologies. Then the next step is I'll change my directory to the repo and install the dependencies. Apologies, my cold is really bringing me down. Uh, so currently, it's installing all the dependencies of the project or of the starter template that I've installed. Yes. So when it's done, I'll just open the project with VS Code. Then we can work at it from VS Code. I'll just close this terminal. This data template is very simple. It just contains a ckETH data backend, which is a lib.rs file that has the hello name functionality. But the main tweaking that has been done is on this particular front end section, whereby if you come to the components and header, you'll see the helper contract address has already been integrated over here. So I'll just take you through it later. So once you have cloned the repo and installed all the necessary dependencies, the next step is to now um, just deploy the backend canister to see whether everything works perfectly before we start editing any code or writing our particular code. So I'll come and we have a particular script over here. So is there anyone talking, or do you have any questions? Can you hear someone talking? Oh, okay. I'll assume that's just by accident. Yeah. So for people who have written Rust before, for us to generate the declarations files and also the candid files, we have to create a particular script that allows us to do it faster. So the number of commands that you have to do manually, which it doesn't give like a good developer workflow. So we just put all the commands in this particular bash script file and then run the bash script file. So the first step, in order for us to run the bash script file, is to give permissions to the script. So we'll just write the command chmod, and then sorry, my laptop is hanging a bit. Yeah, just write the command chmod plus x. Then this is the particular bash script file that we'd like to give permission to. Then once we're done with that, we'll start the local replica for the effects on the background. So we'll just write the command dfx start background. Okay, just a second. Just a second. Yes, so we'll write the command dfx start clean background. Okay, my dfx is already running, which is okay. Then the next command that we'll write is we'll deploy now the backend canister. So I'll just copy that command. Sorry, I will copy this particular command. Just paste it on the terminal. So it generates the candid files over here, or rather the candid file. Then this particular function generates the declaration files, and then the final dfx command just deploys the backend canister locally. So as it's doing that, I'll just open a new terminal. Then I'll start the front end section. So I'll just do npm start. But first of all, I have to wait for it to complete, because if I start the front end server without generating the declarations files, it will bring an error that the did files cannot be found. So it normally takes some bit of time, around 30 seconds to 1 minute, of which it's not that much overweight. So as it generates the declarations and deploys the canister locally, we'll just go through the front end section. So we have a number of functions in the front end part that allows us to interact with the helper smart contract that is deployed on Ethereum. So this particular helper smart contract is deployed on Sepolia, Ethereum Sepolia. So we're interacting with the testnet version and not the mainnet version, because of we don't like, if you interact with the one on the mainnet version, you'll have to spend a lot of money on it. So we're just using the testnet version for now. So the first function is this one, which is calling the deposit function on the helper smart contract. So it's just calling, as you can see, the function name is deposit. The value is this amount of ether that has been declared on the MetaMask wallet. Then on success, this is what will be displayed, and on error, this is what will be displayed. So yeah, so this is ideally the main function that's required whenever you are starting to now interact with ckETH. Once I can see that my backend has been deployed, so I'll just npm run start. Then I'll open it in localhost. Yes, so this is how it looks like. The functions cannot work for now because we haven't integrated them to the backend canister, or we haven't created the functions in the backend canister yet. But over here, we've already implemented the connect wallet functionality, so I'm able to connect my preferred wallet of choice. So for me, I use MetaMask. So I'll just connect it. Just put in my password. Yes, and once it's connected, it will tell you, like, it will show you the connected wallet address. So once you're done with that, the next step is to now write the backend the backend logic for interacting with ckETH. So the first step is to, of course, we'll go to the lib.rs file, and we'll just remove this function at all completely. Now the first step is to generate a sub account from a principal ID. So what's happening, or what exactly we are doing is, in order for us to get the deposit principal that we need to attach to deposit it onto it, so that that particular principal holds ckETH, we have to generate a sub account from it. And in order to do this, there are a few steps to follow. The first one is we are using a dependency called b3 utils. So I'll just get the dependency and attach it over here on my cargo.toml file. Then it will automatically just add the dependency to my directory. Then the next step is to insert that particular function that is responsible for generating the sub account, in order for us to use it to send it to it, for ckETH to be minted to it. So we will import a few dependencies. So I'm just directly copy pasting all the required dependencies, and also the functions, for the purpose of time. But everything can be found on the documentation, of which I will send immediately after this call. Yeah. So the first function that we will create is called the canister deposit principal, which is responsible for now creating the deposit principal from our particular canister ID. So I will save it. I just hope it saves without any errors. So I'm waiting for the Rust analyzer to do its thing. Yeah, so just to explain to you what this function does is, it creates a sub account from the canister ID. So over here, we're using the Internet Computer CDK to get the canister ID of our canister that has been deployed. Then it creates a bytes 32 vector from the sub account, and then using the function vec to hex string with OX from the bit3 utils cargo package, we are converting that bytes 32 into now the deposit principal that we use um, to deposit it to it. So once this has been done, we will now redeploy the canister. So I'll just come and d.sh, then if generate ck start backend, then dfx deploy. So it's deploying it. Once it has deployed it, I've already integrated this function on the front end part. So over here on line 8, you can see we've already imported the declarations file over here. Then this is the function that we're using for to get the canister deposit address. So you can see it calls the ckETH starter backend file, then it gets the canister deposit principal. So this is the function that we just created right now on our backend canister. Then using the state variables, it adds the deposit principal to this particular state. So it's taking some bit of time, which is it's okay. So once you've written that particular function, the next step is to mint ckETH tokens to the principal ID that has just been generated. So for minting the ckETH tokens, all the contract information can be found in this particular folder. Not this one, but this one, contracts. So if you come to SRC components contracts and come to the contract address, you can see the minter helper contract address that is responsible for for holding the ETH. And then you can also find the ABI. So for people who are a bit familiar with deploying smart contracts on EVM-based chains, you know that we normally have like the contract address and the ABI, which allows us to interact with the. I lost my screen for a second. I don't know whether it's still visible. Yeah, I think it's visible. So we have like the contract address and the ABI that allows us to interact with the with an INI, with the smart contract that has been deployed on Ethereum, on Polygon, or any of the NINI of the EVM based chain. So it has successfully deployed it. So if I follow the URL, yeah, and I call this particular function, it will generate for me now the canister. So this is the particular deposit principal that is required for us to send it to it. So if I come to my front end part and decide to call this part or to press this button, we can see it now fetches the canister, the deposit address from my backend canister, and displays it to the front end section of my project. So once you've done this, the next step is ideally just to minting the ckETH tokens to the deposit principal. So I'll come over here and input the amount of tokens that I'd like to mint. So 0.000, let me say 2, and I will press the deposit button. So a MetaMask wallet pop-up is supposed to appear. Yes, here it is. And it will wait for me to approve the transaction. So I'll just click on confirm, and as you can see, it's sending the ETH to the helper smart contract so that the minter canister can just not the minter but the ledger canister can can listen for the received ETH function, and then mint the amount of ckETH to this particular deposit address. So the function has run successfully. I'll just try to, let me see whether I can get it on Sepolia. Let us go. So what I'm doing is I'm searching for my particular wallet address to see the latest transaction that has been done from it, just to verify whether the transaction has occurred or has happened successfully. So it's taking some bit of time. Okay. In the meantime, we'll now create a function that is responsible for verifying the transaction on chain. So after minting the ckETH, it's very crucial to verify the transaction on chain, and it involves checking a number of details, which is the transaction status from the transaction log, the to address, which must match the particular minter address, and also checking whether the logs include this particular deposit principal, this one, this deposit principal that we were able to generate. So if I come over here, just to renew, we can see the transaction has happened, and this is a transaction hash. So if I click on this particular address, it will take me to the helper smart contract address on Sepolia. We won't dwell on that for now. Yes, we'll just let's now create the function that's responsible for verifying the transaction on chain. So we need to add a few packages also to our backend canister. The first one is sad and sad JSON. Yeah. Then the other thing is we need to create a few structs that are responsible for handling the transaction hash that is gotten, or the receipt that is gotten from the transaction hash. So there is no need of you guys like hard coding this. You'll just come and create a new file called receipt.rs. Then just all this information is then in the documentation. We copy the different structs that are there. We have a struct for the log entry, we have a struct for the receipt wrapper, we have the transaction receipt data struct, and we have the verified transaction details struct. So once we've copied it, we need to come and now import this particular receipt.rs module to our lib.rs file, so that we're able to use like the different structs that have been created on the receipt.rs file. So once we've done that, the next thing is we need to install a few packages that allows us to interact with the EVM RPC canister. So for us to verify the transaction on chain, we need the EVM RPC canister to help us call the Ethereum JSON RPC providers. So we have a few packages that have been created that allows us to directly interact with the EVM RPC canister. We have the IC EVM utils and the EVM RPC canister types. if you feel like this is a lot, don't worry. I'll just send the documentation immediately after this call, and you guys can just follow along with that particular documentation, because it has clearly stated everything. So once we've installed the packages for the EVM RPC canister, the next step is to, because now we'll be using the EVM RPC canister locally on our end, since we're not deploying it on chain, we have to declare the, or rather we have to add the EVM RPC canister in our DFX JSON file. So I'll just come and directly copy the EVM RPC canister, then I'll just add it over here. Yes, and you can see we have the canister ID. So this is the ID. This is a specific ID that's present on the mainnet, but it will also be present for us on the on our local version, because we've specified the ID over here, and we have the initial arguments, which involves declaring the number of nodes in the subnet, which is 28. So ideally, what you'll just do after this is just DFX deploy EVM RPC canister, and yeah, you're done. Then after we've added the EVM RPC canister to a JSON file, the next step is to import all the required dependencies to our lib.rs file. So the dependencies that we'll need from the EVM RPC canister, types dependency that we just installed, and also we need to instantiate our EVM RPC canister. So in order for us to import the dependencies, or I'll just copy the code for importing all the dependencies and add it over here. Then I will come and now initialize the EVM RPC canister by declaring its canister ID. Yes. So once the EVM RPC canister has been initialized, the next step is to define the maintainer address for now ckETH, but in this context it's ckCepolia.eth. So we'll just come and define the maintainer address, which is this particular address. As you can see, this address matches the yes, it matches this particular address over here. Yeah, it matches this particular address over here on Sepolia Etherscan. So once we've already defined the address, the next step is to we need to create a function that converts the transaction receipt into a receipt wrapper in order to help us like properly handle the response. So I'll just come and quickly create that function. So the main purpose of this particular function is to enable us handle the response correctly, and also display it on our on the front end side. So after you've already created this function that's responsible for handling the result, now we need to create a function that that is responsible for getting the transaction receipt and the transaction hash. I will name the function eth get transaction receipt, and I'll just come and add it over here. Yeah. So how it works is it utilizes the EVM RPC canister and makes a call to it, and the specific function that it calls from the EVM RPC canister is the eth underscore get transaction receipt, and it makes the call to different RPC providers, of which you can see over here. We're using Anchor, we're using BlockPi, and I think I just lost my screen again. Okay, it's back. And public node. So we're using those different the reason we are fetching the results from these multiple RPC providers is in order to ensure that concept of this decentralization still exists, because it's a low chance, but there's a likelihood that we might have like malicious actors who might tend to change the data of that particular transaction hash or transaction receipt. So we are calling different RPC providers. Then once we've called the RPC providers, over here we are comparing the results. So as you can see over here, we are using the multi-get transaction receipt result from the EVM RPC canister type to compare the results. So if the results are consistent, we will now return the receipt. As you can see, we're returning the receipt over here. But if the if the results from these different RPC providers are not consistent, it returns an error. The error is called the error is formatted in like EVM RPC returned inconsistent results, and the function won't run successfully. So once we've created this function that gets the transaction receipt, the next function that we are supposed to create is now the function that's responsible for verifying the transaction on chain. So the name of the function is, we will call it verify transaction. So just come here below my canister deposit principal and write the function over there, and it's an update function. So what this function, what it does, it gets the its transaction receipt. As you can see, it calls this particular function that we just created. Then once it has gotten the receipt, it extracts the the receipt, the data from the receipt using this particular logic. Once it has extracted it, it now compares it now checks the transaction log from the receipt data. So the first thing that it will check is the status of the transaction. So as you can see over here, we defined our success status as, this is just one. So if the status, if the status of the receipt data is 1, oh my god, I'm losing my voice. If the status of the receipt data is 1, then the transaction is true. So this logic is checking whether the status is 1 or not. So if it's not 1, it will return an error that the transaction failed. Then it's checking the to address. So this to address is the minter address that we just defined on top over here, which is the minter address for the CK Sepolia ETH. So if the to minter address isn't if the two doesn't match the minter address, so it also returns an error that the minter address does not match. Then once it has successfully this particular logics have successfully passed, it returns the receipt data. So as you can see, it returns the to receipt, the status, the transaction hash, the block number, the from, and the different the logs, the address and topics logs from the receipt data. So once we are done with this, the next step will be now deploying it locally in order to test it. I hope I am still audible, regardless of whether my voice is misbehaving. Someone can just confirm.
You're audible. You're audible enough.
Okay. Yeah, so, sorry about that. I didn't know my voice will misbehave like this. So once we're done with that, the next step is now redeploying the canisters, including the EVM RPC canister that we just added to our project. So I'll just come on my terminal and redeploy everything, and now test out the verified transaction. Yes, so we have an error. Which it's okay. So as you can see, we get an error that get random whatever cannot be it's an undeclared crate. So it means we have a certain dependency that we forgot to add to our cargo.toml file, which is called the uh, uh, um, get random dependency. So I'll just come and everything over it's on the documentation that I'll share. Just come and add that particular dependency to my cargo file, and rerun now the commands again. Redeploy the canister locally again. So it's redeploying the canister. It will also take some bit of time because we added a number of dependencies to it, so it has to compile the dependencies before it deploys the canister. Sorry, but I'm almost done. Once I do this, ideally we'll have finished that particular section. Kind of misbehaving. Am I audible? Can you guys still hear me? So my machine is misbehaving. I don't know why. Just let me close VS Code and to open it again. Oh, hi guys. Sorry. My machine just I think it restarted itself. um Sorry. Yeah, my machine just restarted itself, so I'll just quickly turn it on. Just a second. Sometimes these dependencies that we are adding normally tend to get a bit heavy. But for me, it's because I kind of messed up my machine a while back when I was dual booting. So sometimes it tends to misbehave since I didn't assign the right amount of storage to it when dual booting, which it's just still okay. We can just work with that for now. Just a second. But one of the most interesting things with when you're dealing with ckETH is that the end user doesn't have to know that they're actually handling ckETH or they're actually interacting with ckETH. So this is very beneficial whenever you're creating multi-chain projects. So let's say the user that's going to use your particular application or your particular dApp is someone who has never interacted with internet computer before, or rather ICP before. So for them, giving them like new concepts such as ckETH tokens and all that will be kind of cumbersome. So when you're like implementing ckETH on your particular dApp or on your particular canister, the end user themselves, they actually have no idea that they're interacting with ckETH, although under the hood it's actually utilizing ckETH, which is quite a game changer, because now when it comes to the other different tokens that exist, such as the wrapped tokens, wrapped BTC, all that, you find that yes, sorry, I got disconnected for a second. You find that the user, they actually know that they're interacting with like wrapped tokens and all that, because of the whole concept of they have to bridge the tokens, and they have to bridging in order to convert their, like, for example, Bitcoin tokens into now wrapped Bitcoin. Yeah. So as we wind up, I will rerun the command for deploying the canister locally. Yeah, so as it deploys the canister locally, just to mention, so this particular logic, you're actually free to um, tweak them according to your project requirements or project specifications. Maybe you are creating, let's say for example, a crowdfunding app of which it's utilizing ckETH, so it's targeting the people who hold ETH, and under the hood it's utilizing ckETH. So especially in this particular function over here, the verified transaction. So once you've actually verified that the transaction is true, you can now add like your particular logic that you need to add for your dApp. Let's say mapping the amount of ETH that has been sent, um, the amount of ETH that has been sent to the specific, like the specific ID of which that particular person had received the ETH. So depending on the logic for your particular smart contract, you're free to tweak this particular backend logic to suit that particular architecture, that particular logic. So as it finishes deploying it, we'll just write the final section of the code, which is now fetching the canisters ckETH balance and performing transfer functionalities. So once you have verified the transaction and all that, um, how we can get like the how we can fetch the canister ckETH balance and display it is we use a number of packages, of which we have already installed them. So on the B3 utils package, we have like a ledger section that has different tracks that we can use to get the to get the the account, and also the transfer arguments and the transfer result for now a particular ICRC ledger canister that we're interacting with. Then we also have the intercall and call cycles APIs that are required whenever you're performing transfer interactions. So once you've imported the dependencies from the b3 utils package, the next step is you need to define the ledger canister ID responsible for withdrawing and transferring of ckETH, and also the minter canister ID that is responsible for minting and burning of ckETH tokens. So we'll just come over here just below the minter address and define those two addresses. So the ledger canister ID and the minter canister ID. Then the next step is we have to create another module that is called minter. So we'll just call it minter.rs, which is responsible for it allows us to create the different structs that are required for displaying the results from the minting and withdrawal of ckETH from our canister. So once I've already added the content, just come and import the module over here. So module minter. Then once I'm done with that. Now I can implement the function for fetching the balance of my ckETH balance, and the function for implementing transfer of ckETH from one particular address to another. So we'll name the first function balance, which is this one. So it's responsible for fetching the balance of ckETH. So it utilizes the ICRC account struct from our b3 utils ledger package, and so it creates a new ICRC account from our canister ID. Then once it has created the ICRC account, it fetches the balance of it checks out. You see, this is the ledger canister ID that we just defined over here. It comes, checks the ledger canister ID, then fetches the balance of the account that we just gotten by calling the canister ID, then returns the account the balance of this particular account, which is the balance of our canister ID. So also for this particular function, you are free to tweak it based on the logic that you had created for your for your smart contract or your dApp. So the next function that we'll create is now the transfer function, which is responsible for transferring a certain amount of ckETH to a particular principal ID. So you can see it takes two arguments. The first one is a 2, which is a string representing the principal ID. Then the second argument is now the amount of ckETH tokens that you'd like to transfer. So it creates an ICRC account from the two address that you just inputted into it. Then it comes, we now define the transfer arguments using the ICRC1 transfer arguments tracked from the b3 utils package that we just installed a while back. So from sub account we'll just put none, the fee we put none for now. So these are highly dependent on the logic of the logic that you're writing for a particular dApp. For us, we'll just use none for now because this is just for practice purposes. Then from the ledger canister, of which we had defined it over here, it calls the transfer function from it. Then the argument is obviously the transfer argument. Then if the function runs successfully, it automatically returns the ICRC transfer result as an as the return argument. So just a disclaimer for these particular functions, especially the balance and the transfer, your okay. For the balance, you don't have to have deployed your canister to the mainnet, but for the transfer functionality, since it's still utilizing, it will utilize cycles, a specified amount of cycles. You need to have deployed your canister to the mainnet for it to work. Yes, an error. Okay, I hadn't started my local replica, so don't worry guys, I'm just finishing right now. Sorry about the laptop hiccup. So I'll start my local replica of the effects, then so once the replica start, I will redeploy them. Yeah, so it's deploying all the EVM RPC canister and also the backend canister that we just created. So what I'll do, just because of time, I'll come and directly copy the Sepolia Etherscan, the transaction hash from my. Let me show you guys from the transaction that I did a while back, and just paste it on the function so that you see how it works. So this was the transaction over here. This is the transaction hash. I'll come and copy it. And I'll come to the backend canister URL. So it's loading. Yes, wait, yeah. Then I'll come and put the transaction hash and just call it. And we're crossing our fingers, just hoping it works. Because sometimes it tends to fail. Yeah, it actually works. So as you can see, it has returned the transaction log for this particular transaction, and you can see the two address, which is this particular address that we just sent um, the, 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 the ETH to. This is the helper address that we are using. Then it has a status of 1. This is the status that we're checking on whether the transaction is successful. So this is the transaction hash, which is this one that we just inputted over here. Then we have the from address. So this is the address that just performed the transaction, which was my MetaMask wallet address. Then we have logs, which has different topics, but the most important topic that we're checking is this one over here. So this topic over here, this is the canister deposit principle that we just used. So if I copy this and just do F, if I copy this particular address and just paste it over here, yeah, it's supposed to match this particular address. So it hasn't matched because I redeployed my canister again, which it's completely okay. But yeah, and you can see the address also, and also the block number of the transaction. So displaying this on the front end is very simple. Just come and run and start. So the functions have already been defined for you, or rather the front end configuration has already been done for you. So just come, go to localhost 300. Then let me copy this transaction hash and yes, I'll just put it over here. Then I'll click on verify transaction, so it's verified. Yes, and you can see the transaction is has been verified successfully. And in a nutshell, that's how you implement ckETH in your project. Well, that's how you get started with implementing ckETH in your dApp. I will send all the documentation immediately after this, but everything that I've done has been clearly stated on this particular repo. on the README file. You can just come and follow it. It gives someone a step-by-step guide on how to now implement the ckETH on your dApp, and also it explains in depth the different functionalities that exist. Yeah, all the different functionalities that you write for implementing the ckETH logic to your dApp. And that's it. So I don't know whether we have any questions. We'll also share the recording by tomorrow. I know this it might be a lot for now, but if you just follow it, if you follow the documentation, you follow the slides, and also you follow the recording, you'll just get like the hang of it, because you can't master or grasp it in all of it in one session. Yes, so I'll assume we don't have any questions.
Oh, yeah. Hi, Steve.
Hi.
Yeah. So can we be able to implement this also back from ckETH to ETH?
Yes. You can actually implement it. In order for you to like convert, it's actually on the presentation over here. So in order for you to convert from ckETH to ETH, you need to perform like a withdraw function from your canister to now that particular wallet address that is supposed to receive the ETH. So as you can see, it's stated here that call canister, then we're using the receiver address calling the withdraw ETH function. So just to like show you guys like how the function looks like, everything is in this documentation. So it's over here withdrawing the ckETH from the canister. So this the reason we put this guard over here is just to ensure that specified principal IDs can only call this function, because this involves you like a user sending or withdrawing ckETH to their wallet address. So it has like the withdraw arguments, blah blah blah. But you can see over here, this is where the main logic happens. It calls the minter canister, then it specifically calls the withdraw ETH function from the minter canister, and the withdraw argument has the amount and also the recipient as the arguments. Yeah, so this is how you like implement the withdrawing ckETH from a particular canister to your particular wallet address. Does that answer you?
Yeah. Thank you. I'll follow up from there.
Yeah. So
on the docs.
yeah. So if you got stuck anywhere, or if you got lost anywhere, everything is clearly highlighted in this particular documentation. Okay, awesome. I think we'll end the session over there. Thank you guys for staying with me up to now. Yeah, and bearing my cold and my scratchy voice. Anyway, thank you so much for joining the call. We'll send all the documentations immediately after this call, and the recording will be shared by tomorrow. Have a good night.